Okay, so today we were going to look over the second chapter. It's about 20 pages, so probably denser than the first chapter, but we can try to see if we can get through it. The page numbering is different than, oh well, let's see. Oh, I didn't notice this part. Part 1 of the book starts with chapter 2. Anyway, anybody have anything they want to say before we go ahead and dive into the reading?
Yep. I would like to give a brief overview of what we are going to go through. So there are basically 4 algorithms: the epsilon greedy, the gradient bandit, the greedy with optimistic initialization, and a UCB that we will be going through. And it's all about bandits in the case of tabular settings. So, yep.
Okay, so, what is a bandit? If you just briefly explain that.
Bandit, you can hear in this respect, bandits is a kind of a octopus. You can take a reference from that, in which you have multiple arms, and uh, uh, suppose the action and the states, and sorry, the if you have an octopus, you want your algorithm to do a particular task, and you have a probability distribution of, suppose, for an octopus you have 8 arms. So uh, with respect to your prediction of the next step that you are going to take based on the previous actions and the reward formulation that you had, you need to select an arm in the next time step. So you can think of it as an association with an octopus. How do you uh, generalize a problem in that respect?
Is the association with the octopus in the sense that an octopus uses their arms, uses their tentacles to explore their environment?
Yes, yes.
Okay.
It's a slim. It can be a same analogy to a slot machine too, with respect to, yeah. So instead you can have a K on levels, or however there may be with respect to the slots that you pull.
I was going to go through all of this later, Joseph, after the reading.
Sounds good. All right, let's go ahead and dive in. Let's read for 15 minutes and then we'll, well, let's see, let's read for a whole hour and then we'll discuss afterwards. Okay, starting now. Okay, we're back. I hope everyone got a chance to dig into that chapter. I myself didn't quite finish it, but there's a lot of math to get through and so on. A lot of thinking to do about some of these equations that we encounter. But anyway, we can start our discussion. Oops.
Yeah, Joseph, I was gonna just run through it. I just made some bullet points or whatever about each of the sections. Like Ali was going to take over the second half of it.
Super.
If that's okay.
Yeah, sounds fine.
Can I share my screen then here?
Yes, let me stop sharing mine. Go ahead.
Can you see that?
Yep.
Yeah, so this is the octopus that Mayank was talking about before.
Yep.
So I'm not sure what you call these in America, but like in Britain, these are fruit machines or slot machines or one-arm bandits.
Yeah, I think they call them the same thing here.
Yep. Yeah, so like basically the problem's just uses these to illustrate it. Effectively, the problem is just when you have like a set of choices with each of the choices has like an underlying probability of having a payout, but you don't know like up front what those probabilities are. And so the whole thing about it is a way to sort of make your selections to try to maximize your payout. So yeah, like the octopus thing is sort of a general illustration just because the fact it's got like multiple arms and it's got to decide which arm to pull next to like try and win some money from one of these slot machines. Yeah, so the K-arm bandit, as I say, it's like when you've got like various choices and you're trying to get the highest reward over several time steps. So like in practice, it's used for sort of various things. Like one of its main uses would be for like website testing, when you've got like, say, like a couple of versions of your website and you don't know which one is going to maximize the conversion rate or the click-through rate or whatever. In years gone by, they would have just like stuck up like one website and then monitored that for a while and seen how much money it would have made. And then they would have tried the second one. But the problem is if your second one is rubbish, your like actual sort of profits will plunge or whatever. Whereas like by using like a bandit approach, you can have like both of them running side by side. So like one user would get one version of the website, the second user would get the other version. And like over time, you gradually increase the one that's sort of showing the best conversion rate. Similarly, like in drug testing, like when you've got like a new drug to put on the market or several drugs, you don't know like which version is the best. So you want to sort of monitor the effect of it. So you would sort of have it for like if the patient lives or dies or whatever. So I've actually got like an example of that here. Let's see. Yeah, so like this here is using like a bandit algorithm to test 5 separate drugs. So here we've got like 5 drugs and we've got 50 patients. Each drug, it either kills the patient or the patient lives. So effectively you want to find out which of these drugs is the best drug to give. So like the whole bandit thing is like to find the strategy which finds the best of these drugs out of the 5 possible ones. So if I like try these here, so if I use just like a simple strategy to start with, so I'll try drug 1. So you can see I've given drug 1 to the first patient and unfortunately the patient died. So obviously drug 1's not very good. So I'll try drug 2. Yeah, so in this case here, the patient lived, so drug 2, it's possibly a good one. I'll continue on. Drug 3 killed the patient. Drug 4, the patient lived. And drug 5, the patient lived. So here, now the problem is, so you can see here, like that 1 and 3, the patient died. So potentially those are bad drugs, but then at the same time, I've only tried it once. So you don't know for definite if they're bad drugs. These other three, I might have just got lucky. So I'll try the three that, yes, like drug 2, the patient lived, so I'll try that one again. Oh, this time it died. So drug 2 is potentially bad. So I'll try drug 4, the patient lived. And drug 5, the patient lived. So drug 4 or drug 5 could potentially be the best. Then again, like the other 3, they might have just had bad trials, but I'll stick with these ones for now. So this one's live. So drug 4 is looking pretty good, but I haven't tried drug 5 in a while. So, okay, so like drug 5 after a while died. So I'll go back to drug 4 and put, oh, then we died here. I'll try drug 2 again. Oh, no, it's not very good. So I'll stick with drug 4. So we've got 50 trials. Maybe try drug 5 again. So here we go. After you've like run this test, this pops up like with the actual sort of efficacies of like each of the drugs. So it did turn out that the one I was trying the most, drug 4, is actually like the best drug, and drug 5 was slightly worse, but still pretty good. So like the strategy I chose there wasn't actually too bad. So you can see here in this graph over the 50 trials. So like over the 50 trials, it shows you like how some of the various bandit strategies get on. So like in my case, purple is my one. So you can see I did pretty well there. Green is the greedy strategy, which we'll get onto like all of these in a while, but like these are sort of 4 various strategies that are employed regularly for like this problem. So like greedy, we'll come on to it, like, but effectively it is when you encounter one of the things that's good, you just like stick with that one. And so you don't do any exploration, you just exploit. So greedy has the possibility of like, obviously if it finds something that it thinks is good early on, but which isn't actually the best one, then it could end up giving like poor results because of the fact that like it sticks with a suboptimal choice. Whereas epsilon greedy, it adds in like a bit of exploration. And so like over time, epsilon greedy will actually find the true probability for each of your available choices. But its downside is it sort of carries out exploration even after it knows that some things aren't so good. The upper confidence bounds one, it sort of balances between the two, and it's like a sort of more sophisticated version of epsilon greedy. And posterior sampling, it's not really touched on in the Sutton and Bardo book. It's like effectively Bayesian sampling. It uses like the probability distributions as opposed to just the mean. So these are sort of the algorithms that we're going to look at. So this just gives like a rough idea of how sort of they vary and how what the problem really is. In this case here, the problem, this is what's called like a Bernoulli Bandit, where there's only 2 possible choices. It was either live or die. Whereas in the Sutton and Bardo book, they're dealing with like the Gaussian problem, where you have like a range of various outcomes. So the problem is, and the reason that they have this put in the book at all is because of the fact that basically the bandit problem is a very simple like illustration of the full reinforcement learning problem. When we get onto the full reinforcement learning, you're dealing with states, and like in a state there's possible actions. So like the bandit problem is effectively just a single state where you have like various choices to make. And so like
Steve, do you have any clue why the why the Bayesian method doesn't beat the epsilon greedy bandit?
Oh, basically in this case here, they're only doing it for 1 run, which is why. So normally so like here, I think that they're a greedy algorithm. It's just got lucky. It's got lucky and like it's found a good choice right at the start. And so it's ended up at the best. So that's what can happen. Like because of the fact we've only got like 5 choices here, it doesn't have sort of much to choose from. And so like it's possible for it to sort of like lock on to a good solution. If I was to run that again, if you were to run this over like say like 100 different goes, you would end up probably, I would say like the posterior sampling would be the best by far, followed by the UCB, followed by epsilon greedy. So it's just because of the fact that it's only just taken over a single test is, I think, what's the problem. So yeah, like the greedy one can be the winner because of the fact that as soon as it locks onto something it finds good, it'll stick with it. So like in this case here, if it came down and sort of tried like number 4 as its first choice, then it would stick with number 4. And obviously over the time, like over the 50 runs of the experiment, then it would by far have the highest total. Whereas like the other algorithms are all doing like a bit of exploration. So that's just why it is at the minute. It's like basically if you had like longer trials and more choices, then the more sophisticated algorithms would be the winners.
Thanks.
Yeah, so that's just a summary of the problem. Basically, you've got like k different choices. In that case, we had 5 different choices. And like the objective is to try and get the maximum reward over however many time steps you're running for. Yeah, so like each of the possible choices, it has like a true mean value. So like this would be the true mean of the underlying distribution. So it's just the expected reward. So if you take action A at time t, you'll get reward t. And this is like the true mean of the distribution. So like this is what you're effectively trying to estimate or to model. So if you knew this up front, it'd be easy because of the fact you would just pick the algorithm or the bandit which had the highest mean. But the trouble is you don't know this. So you need to like try and estimate that to sort of make your choices. Yeah, so like the true mean is like lowercase q star, whereas your estimate is like uppercase qt. So like at time t for action A, this is like your estimated value of the reward that the action is going to give you. And yeah, so as we said already, if you choose the action which has the highest value, then that's said to be acting greedily. And the value that has the highest choice at like the highest value at like at any time step, that is the greedy action. So yeah, so like the greedy algorithm, it just exploits the information it has. So in the drug trial there, after it had sort of performed a few trials or whatever, the greedy algorithm would just exploit that information. It would always just keep on picking the action which gave it the maximum return of the reward. Whereas like the other ones add in like exploration because they say, well, I mightn't have found the best one yet. And so like they look to see, can they find a better choice? Yeah, and action value methods. So as we saw, basically the true value of any of your actions is like the sort of the mean value. And so like it's possible to form an estimate just by taking the average of the rewards you've seen so far. So like every time you get a reward from a possible action, you just add it up, take the average value, and that gives you like an estimate of how good that action is. Yeah, the greedy algorithm then just takes that value, and for any time step, it just picks the action with the highest value. So as we saw, like in that one, it can do pretty well in that it exploits that knowledge, and so like if it finds the best action, then it'll continue to choose that one, and so like it ends up, it gives you a maximum reward that's pretty good. The trouble is if it finds bad choices, it never looks for anything that's better. Yeah, so to get around the fact that the greedy algorithm doesn't have any exploration, epsilon greedy just adds in some like a random element of exploration. So like on every time step with a probability of epsilon, it will sort of pick one of the actions at random. and then does exploration that way. And so on a regular time step, the default action is just to choose greedily, to like pick the one that you have so far, which has the highest return. And then with epsilon probability, you would choose one of the others. And the point is here that if you decide not to choose the greedy action, then you choose randomly across all of the other ones. So the action that is a greedy action can still be chosen as part of like the random epsilon choice. The downside of this one is, although like it adds exploration, that probability sort of never varies really. In the basic epsilon greedy algorithm, even like after you've found that some of the actions are rubbish or whatever, you still sort of continue to choose them. The basic version of this just keeps on trying, just randomly picking the actions.
Is there a variation that actually looks at what you've done in the past and chooses the optimal action from looking at the probability distributions, or the in other words, if it finds that action 2 got rewards 90% of the time, then it would more likely choose action 2 than action 3, which only got good rewards 30% of the time?
Yeah, there are, like, that's effectively like what the upper confidence bound one does, which
Okay.
we'll come on to. But there are, simpler versions of it, which are simpler versions of like epsilon greedy, where over time you would decrease epsilon. And so by decreasing epsilon, then your chances of sort of choosing one of the random actions decreases. And yeah, there's other versions as well, which, as you say, like sort of if something is sort of showing like really bad performance or whatever, then you exclude that one from the choices that you make.
Or in general, you just look at the probability distribution you look at the reward distribution of each past step, and then you choose your next step based on how good each one has performed in the past. So you don't ignore the past. In other words, it would seem like that's another possible way to explore.
Yes, that was like also covered in the book. In the he dealt with it like within sort of the terms of non-stationarity, where your sort of probability is varying with time, but like effectively you can like use like a weighted sum. So
I see. If the probability, if the thing is non-stationary, then what I just said doesn't work very well, because the things change with time.
Well, that's why, so by like using a sort of weight for giving more weight to like the recent stuff, and like less weight to like the far away stuff, then stuff that happened far into the past, it sort of gets excluded. And so you give more weight to the recent stuff. So as well as dealing with like the non-stationary things, it is used like a lot in just reinforcement learning in general to sort of give more weight to things that have happened recently.
Yeah.
I had a question. So how important it is to like correctly being able to devise these rewards? For example, I can see how this algorithm can break if the patient dying had 0 reward instead of a -1. So like probably the greedy algorithm could easily fall into like a local optima solution, right?
Again, like it's something that's general to all the reinforcement learning. It's like it's very important to decide sort of how you allocate the rewards and what you use as your reward. Like for example, in a game of chess or something, quite often they would just use sort of giving a reward only if you win the game, whereas like in early sort of attempts at that, they sort of used other variations of rewards, where they would give like a reward for having the most pieces or taking pieces and things. And it ended up like the algorithm did sort of strange things in that rather than winning the game, it just like went out to try and capture as many pieces as possible. And so it's very, very important to decide what your reward is, and sort of to make sure that the reward that you're using actually identifies your end goal. So
is there like a specific process to devise this reward, or is it like trial and error based? That's what I was trying to ask.
I would on page number 33 on the book, there is a equation 2.7, which gives a solution to this problem. Here they have defined two conditions. The first condition, that is that, as you said, was required to guarantee that the steps were large enough to overcome any initial conditions of local optima, or the random fluctuations that happen. And the next condition here guarantees that the step sizes become small enough to reach the assured convergence. So this is one of the ways that you can model your algorithm to make sure that both the initial jump from the local optima is kind of like it is able to overcome that barrier, and the next step is with respect to the convergence. So yeah.
Got it. Okay, thank you.
Okay. Yeah, so also in the book, he sort of like goes through the algorithm about how to sort of calculate your new value. Obviously, because of the fact that our estimated value is basically just the mean of the rewards that we've seen up to that point. One way to calculate the mean would be to store all the past rewards, but that obviously sort of has implications from computing power or whatever. As time goes on, eventually your computer will run out of memory. And so it is possible just to calculate the new estimate of your return from the previous estimate. So this is like the return at like n+1. And like this is the return at the previous time step. And like this is the new reward. So just by holding like the number of times an action has been tried and the current reward that you've just received, you can form your new estimate. And again, this type of like update step is used through all of reinforcement learning. It's not just for bandits. Yeah, and the final algorithm I'm going to look at before passing over to Ali is like the optimistic greedy one. This is the graph here shows, yeah, like there's a 10 arm bandit problem, like taken from the Sutton and Bardo book. So you can see here for each of the available actions, each has an underlying probability distribution with like a random mean. So like in this case, what's this? Action number 3 is the best. Normally, like if you were just running the greedy algorithm, you would start with your estimates all at 0. And so like what would happen would be if the bandits or if the algorithm just tried the first action number 1, it would get it like this sort of slight reward. But because of the fact that the slight reward is better than all the other initial estimates of 0, then it would like stick on this action for the future. And so over like all of the time steps, its total return would be rather low. Whereas like by having like an optimistic greedy, in their case, they started the optimistic greedy up here at 5. So like in this case, what this forces to happen for like the initial sort of K steps, where in this case K is 10, it'll try each of the actions. So here it'll start at 5, and if it tries action number 1, it'll get whatever that is, like 0.2 plus 5. So like an average of about, I don't know, well, that is 2 or something. So it'll be dropping down here. It comes to this one and tries 5. So again, like this will like end up like dropping the average down quite significantly. So like over the first 10 runs, each of the actions will be tried once And like at that point already, like these ones here, if they return something close to their true mean, they'll like already be excluded from the sort of the selection process. And like this works pretty well because it ends up like anything that's actually sort of below the mean of the optimal action, it's quickly discarded. And so yeah, like the optimal action is like sort of quickly locked onto by using this strategy. The downside of this is because of the fact that the exploration only ever happens once, right at the start. Once it's sort of like locked onto things, it never looks for anything else, and there's no more exploration that's done after that. So yeah, again, as it says in the book, it's not good for non-stationary situations where the probability or the mean values are changing with time.
So I'm not sure if this makes sense, but if you have a non-stationary situation, couldn't you just at random intervals just punch the reward up, punch the initialization up, to 5 or whatever, and then let it go for a while, and then do it again and again and again, and that would.
You could possibly, but like it's like, when do you do that? And yeah, so like with that approach, you would have sort of two sort of questions. It'd be like, how often would you do that? Because effectively you're going back to sort of putting yourself back to the start. Mm-hmm. And the other problem like the optimistic greedy has is just deciding on what your initial value is. Because the trouble is, if you choose a value that's like much bigger than like the true values that your actions are returning, then it takes like a long time to get down from the sort of initial value down to like the true values. Whereas if you choose like an initial value that isn't high enough, like say you choose like 1, in that case, then you might again miss sort of finding the best one. And so, yeah, I think they said like optimistic greedy is basically just good for sort of simple cases. There's like better approaches to take for like environments where like the actions can change over time. Yeah, so sorry, I better stop here and swap over to Ali because I've gone over my time. So I'll stop sharing and let Ali take over for the rest of it.
Hi guys. So just one second, I'll share my screen. So is my screen visible?
Yep.
Mm-hmm. Hi. So the main thing, I don't have a PowerPoint like Steve, but the main 3 things which I'll be explaining is one is upper confidence bound. So main problem with other things were that it was exploring, but how do you make sure that we explore in a proper manner? That means make sure that we explore things in which we are not in having greedy, but as well as finding some fine tuning and exploration. So that's where the upper confidence bound comes in, where we try to find non-greedy actions, and according to their potential we find, okay, let's be optimal and do some greedy methods. So the main thing here what we have is the equation where it tries to say that for the maximum we want to get the maximum confidence out of exploration. So where QFT is the event for the step, and T is the discrete time, and the number of times we have selected that's we have that selection in the past, and C is the parameter which we give. So if we try to see that in the past events, if we have selected any example as 2, as Steve had shown 5 medicines, if you had selected 2 second medicine a lot, so this number will increase, and in that manner the confidence value will slightly go lesser because of the square root problem. So in a small slide where of the University Berkeley lectures, where they try to explain confidence value, where if the number is small, the automatically the confidence value increases a lot, saying that okay, this we can check this out more. And with that, the exploration part happens and the confidence starts increasing, where the uncertainty, we have high uncertainty in those options. And using that, with the maximum value, we try to find we try to select the event and we move forward. So there's a small graph where in the book they try to share that how as steps are increasing, it tries to how should I say tries to explore, and it takes a dip with respect to explore and greedy. But as all of a sudden it takes a spike and gradually it increases. So the exercise was that giving we have to give us a very satisfactory explanation that why this is happening, and I couldn't find if someone who knows could explain and say why this was happening. And hello.
Yeah, we can hear you. We can hear you.
So here's where I couldn't give a proper explanation for why the reward increase at the 11th step. So this is one exercise which the author has given the readers to solve. And
It's because of the argmax, since and it's an optimal policy, which the initial what they do is initially the number of steps that they take. It's a purely optimistic version. So you can say they have uh, how do I put it? Uh, uh, Much better action value estimates in the uh, initial time, as I think so. Uh, Steve also alluded to with respect to the examples that he had shown. So that's one of the reasons, because the large rewards that it gets based on the initial draws, uh, uh, which may be having a good initial policy or the reward. So the accumulation will be large, but afterwards, after the 10th step, most probably the 11th one might have uh, action that it explored that might not be optimal there. So uh, that's the reason why.
okay, got it. So does it also mean that it explores all the 10? Because usually what happens here is the occurrence of each event will be zero at first, and the confidence slowly it decreases as it increases, because there'll be one value which will already be stated if it is zero, because if the divisor is zero, it becomes infinity, to make sure that that mathematical problem is not considered while evaluating. Does that also come into the picture?
Yeah, they say there that, yeah, so like in this case with 10 actions, each of the 10 actions will be selected once within the first 10 time steps. Yeah, so they say like when the number of selections is zero, and as you say, it would be infinity, then they make that action selected.
Cool. So due to this reason, they try to explain what UCB high confidence bound value slowly is better than E-greedy. It shows nice average performance is better. And after this, it's a very math heavy. gradient bandit algorithms where they try to give more action based on the preferences, not on in terms of interpretation and rewards, where they try to use softmax on the reward provided on the each event. And there he tries to even explain how give a proper induction derivation of how how the present reward will is affected by previous reward as well. And I'm not good at explaining mathematical stuff, so I would suggest someone better than me to explain this later on. And here's how he tries to explain with giving a baseline while evaluating optimal solutions, where this RT is average of mean average of the rewards accumulated in the past whole events. So this is a baseline where having where without baseline there'll be very bad results in optimal actions, and with baseline it's far better, is what he tried to explain. And this is all stochastic gradient design, how the formulation and decision is happening. And with that,
I'm looking at the his initial discussion of gradient bandit algorithms, and he says that the preference has no interpretation in terms of reward, but that doesn't seem right when you look at equation 2.12, where the preferences are being based on the rewards. So I kind of don't understand why he says that the preference has no interpretation in terms of the reward.
So I believe he means that the preference values are not do not have to be proportional to the reward values, which means say we could have like negative preferences, but it doesn't matter, as we only need it only looks at the ordering of the preferences, right? Not on the relative, not ordering, but relative differences between the preferences. So say you have like I don't know, maybe your reward distribution is very uneven. So you have very high reward for some actions and very low reward for others, but it might not be like the same proportion between the preferences, but still we just we take soft marks of preferences and convert those to probabilities, and so.
But the probabilities there are still being formed in terms of past rewards. So they do depend. It seems to me they do depend on. It's not an independent scheme. It's not independent of rewards, as he says. That
it's not independent, and probably he doesn't mean that. He just means that in all previous algorithms we used reward Q value estimates for decision making, and here we use this H values, which are not estimates of reward. So that's what it means, I guess.
It kind of throws me off because it seems like this approach is actually working to find those choices that do give the best rewards. In other words, it's taking into account the history and trying to find those choices which should lead to the best rewards. And that's an approach that hasn't been tried in the previous in the previous approaches, like upper confidence bound also tries to take into account the previous guesses. But I mean, the first couple of strategies where you do greedy or epsilon greedy, they don't take into account the history. They just try to explore randomly. But in this case, now we're trying to explore based on the best chance of getting a reward. So it kind of throws me off when he says that it's independent of reward. Anyway.
Yep. It also depends upon the number of actions that it has selected. So if we look at equation 2.12, there is a term after alpha, RT minus RT bar, which demonstrates the RT bar is a average of the pivots, but up to the time not including T. So it kind of reduces the variance. Then it only compares between the number of actions. So then it goes on to the how do we say it? The action preference that it had initially selected. So that's the if we go to the graph that is on page number 38 as the figure 2.5. Here they have shown a stochastic approach with respect to some approximations being applied, and the RT bar here is taken as 4 in the upper blue line, I think so. Yeah, and in the lower one, it is taken as 0. So here, that's the difference that the author is trying to say. Uh,
I think this is not a correct interpretation. So he says that the initial values are with means 4 rather than 0, right? And
yep.
Without baselines in both cases mean that our bar would be 0. And with baseline means that we will use the average reward up to this step as baseline.
Yep. Thanks. So yep, but with respect to the baseline, the difference is what this equation 2.12 is trying to model the algorithm on. So it's not directly upon the rewards, but the difference between the baseline and the number of times that action has been selected. So yeah, it's a bit tricky here because when we go to the inner loops, if we try to model that, then yeah, it kind of like depends upon the state and the action and the why the number of actions were initially selected. But yeah, from a top level perspective, it does not have any interpretation on the terms of rewards. It's just that if we go a level deeper and try to understand the intuition behind what was the action preference behind this. So yeah, that's I think so. That's what this gradient-based algorithm is trying to convey.
I had one more question. So what could be the intuitive reason why making RT bar 0 results in like degraded performance? Because the way I'm seeing like non-contextual bandits is it doesn't, the past choices do not affect the current choices, right? So if I make RT bar 0, which means that whatever reward I got in the past is not necessarily something I care about, then why does the performance degrade so much? Or am I thinking about this probably incorrectly?
Yeah, so I experimented a bit with this. I was implementing this stuff in code to see how it works, and I made a small mistake when I didn't pass this +4 to initial. I didn't choose change the initial Q values, like the true distribution, which was which we are trying to estimate during the process. And in that case, actually, in my simulations, the version without baseline. So here, you see the mean Q values would be initialized with mean 0. And this R bar, which I used, was also 0. And in that case, the version without baseline performed better. So basically, I believe he mentions in the book that the choice of baseline to be the average reward up to this step might not be the best choice, but it works somehow. So so this choice is probably not the best, and it depends on the conditions of the problem you face.
So just to understand, you kept the Q initializations to 0, and then you also kept the RT bar as 0 constant, right? So it was basically the brown solid line, the without baseline line was moving up close to with baseline. Is that what you're saying?
Yeah, actually, the version without baseline. So when we just don't subtract anything from our bar at the update, it performed better than the one with baseline. You know, when we subtract an average reward up to this step. And,
got it. Thanks.
Okay, then after bandit gradient algorithm, last one is associative search, that is contextual bandits. So until now, what we were the task which we're talking about is non-associative task. That is, there's no need to think when you are selecting something, a task, or when you're having some selections right now, the past selections won't affect the present one, or there's no context depending. So here associations, one simple example what the author has given us, that where a policy where signal by color. So what he's trying to say is that now we have selections where we have an arm, and if it's red and we select arm 1, and if green we select arm 2. With the right policy we can actually match them better in without any information. But if there's an association search task, not only here should we do trial and error just to search best actions, but even we'll have to think about the association of these actions with respect to the situations where they, whether to find out whether it will be best or not. And that's why these are called contextual bandits. And they are and these associative searches are more or less into, they are in between k-arm bandits and the full reinforcement learning problems. So these things are more talked about in the next chapter, is what they have told. These problems will be talked more about next chapter and taken through the rest of the book. So yeah, this is the end of the chapter 2. I'll be stopping my screen now. That's it from chapter 2, my side. Thank you.
So if we look at figure 6, 2.6, he summarizes comparing simulations with all the techniques we've discussed in the chapter, the epsilon greedy, the gradient bandit, the greedy with optimistic initialization, and the upper confidence bound method. And he finds that the upper confidence bound method does better. But I'm not sure why, but that's what the summary says.
The upper confidence bound algorithm, out of the ones sort of that he's maybe not like that last gradient thing, but out of like the other algorithms, it is sort of the most complex. But as you can see from that graph, the sort of performance depends quite a bit on the parameters that you choose, and you need to sort of have a bit of knowledge to sort of choose those well to get the good performance. Whereas, yeah, like a lot of people, for when they're actually using sort of bandits in the real world, they would use Thompson sampling, which is like the Bayesian approach, which has the benefit of you don't really need to choose any parameters. It sort of works it out for itself by sampling from the probability distributions. And so, yeah, for like the A/B testing stuff I was talking about to start with, yeah, most people would use Thompson sampling in the real world to choose between things. Similarly, the stuff we talked about there at the end about like contextual bandits, people use that in the real world in the to give, you can like give information about the users who are coming to your website to sort of, if you know something about their information, then you can use that as the context to help you decide on your choices.
Yeah, isn't equation 210 the argmax thing with a square root log t over nt? Isn't that the end result of a computation to you can actually figure out the optimal value in that situation? I mean, mathematically, and that this ends up being a variance term. I think I've seen that somewhere. So even though they give you the end equation here, but really they're really saying, hey, this is a mathematically exact kind of thing, and we're just applying it here. I'm pretty sure that that's the case. So therefore, that variance term allows you to get the UCB algorithm, and yet it isn't as practical as the other ones because you have to make a lot of assumptions to get that term, I believe.
Yeah, like in the UCB formula there, effectively it is two halves. Like the first half is your exploitation. It's like the greedy bit. The argmax of the QT is just the greedy formula. Whereas, like, as you say, like the right-hand bit is sort of the uncertainty in your predictions. So yeah, as you sort of select more from a particular action, then your uncertainty drops. And similarly, like,
yeah, I mean, I guess all I was getting at is, I know that's an equation there in the book, but the point is there's some 2-page derivation somewhere that I definitely seen where they derived that. Okay, so yes, there's the equation, but if you want to go deeper, you're going to have to dig into some derivation of that formula involving in that where that second term ends up being the variance. That's all I'm saying.
Well, so this assumes stationarity, right? Because like UCB algorithms also would work on the stationary problem on the right. Because
yeah, like the right-hand side, as you can see, it's got like log t on the top of whatever. So like it's the total, I think it's like the total number of samples. So again, as time progresses, like overall time, not just time in a particular action, the exploration decreases, and so like after a while exploration disappears and it just exploits. So again, if the actions were varying their mean over time, then as you say, yeah, it wouldn't deal with that.
I guess I'm puzzling over the form of the equation where you're saying the argmax of Q. Okay, if I just looked at argmax of QT of A, that would just be the greedy choice. Choose the action that results in the best reward. But adding this kind of, you're adding something to this reward term, and you're saying, okay, now give me the A that gives me the maximum of of qt of a plus this function that depends on time and on the amount of times that a has been used or whatever. I'm just puzzling over the argument within the square brackets, why you would increase that argument and what effect it would have.
I guess I kind of lost your point there, sorry. Just looking at it.
I'm just puzzling over the form of that equation 2.10, that's all. I mean, I just don't quite understand how it works.
Well, it's, I mean, the way I viewed it was that, that one thing it does, right, is it forces you to keep looking for new stuff, because as the number of times the arm gets pulled goes up, you're going to get a smaller
argument
variance term.
Well,
there, right?
I guess it's trying to force you to. This is kind of goes back to what Steve was talking about before, where you initialize by looking for a large reward. What do they call that? Optimistic initialization, right? You look for. So this is a way that maybe this is a way to make that, to extend that process past the initial part of the search, and you're constantly looking for a larger reward, but you're tuning the amount of reward that you're looking for based on
yes, it does
history.
That, right?
Yeah.
I can quickly share a visualization to like give you some intuition about how this function changes depending on number of action taken and time, like total number of action, if you'd like.
Yeah, exactly. Yeah, go ahead.
So I need to share, you need to stop sharing for me to share. So here, can you see this screen?
Yes.
Right. So here, this is like this value we assign to. Let me just here, like. Depending on time, you see this. It begins. It's very large, but then it decays like as at this.
That's the second. That's the second term, right?
Yeah. So that's the value of the second term, and how it. So for the early part. We will have like if we start here from 0, it would be like for 0 it's obviously we divide by 0 and it's super high, right? So for when each action we never took, it has like very high this additional value, so very high value in exploring it. right? And that's why we had that spike on the graph, on that graph, because for first 10 steps, we take different action, and we kind of have some estimate by the 11 steps, we have some estimate of value in each action. But then when we start exploiting, we again come back to the situation when this potential, as you can see here, for when you had like acted just once, it's 2.5, and again it shifts to exploring those actions because the second term again it outweighs the Q estimates in our decision making. And yeah, here is another visualization is how would this how it's called yeah, so this upper confidence bound term, how would it develop with time? So here I just plot, yeah, you can see that as we take more actions of that kind, the value of that second term diminishes.
Yes. So this is exactly what we were talking about earlier, where we were thinking that, yeah, there's a, you know, the optimistic initialization works, but then it doesn't work after you start exploring. But then this is a way to sort of a variation of that does work while you're exploring after the initialization. It just it forces you to keep looking for a larger and larger reward. Oh, not a large. It forces you to keep looking for a larger reward than there would be if you were just looking at the epsilon greedy approach.
Yeah. So with epsilon greedy, there is a problem that we are bounded like by this fact that we select even when we know the optimal action, and we are like quite confident that that's the best action, we still select it with like at most like 1 minus epsilon% of the time,
yeah.
right?
Yeah.
And yeah, so as Steve mentioned, one way to overcome this, one simple way to overcome this would be to decay the epsilon over time. But again, this will not help with this stationary case. So yeah. Here is
you mean non-stationary, right? You mean non-stationary, right?
Yeah, non-stationary. So this is exercise which one, 2.5 from the book, and there he says like run simulation for 10,000 steps, and yeah, as you can see at the beginning, this approach, when we do a sample average for reward estimation, it like kind of works better, but in the case of non-stationary problem, yeah, so at this point it chose some action as to be the best, and it keeps accounting for the rewards we got at the very beginning of the simulation, but as time progresses, those values shifted, but we still give equal weight to old rewards, right? And if we use exponentially moving average instead of sample average, it like picks up slower on the optimal action, but it keeps adjusting it. So the adjusting works much better. So yeah, and that's and here this is why this spike in UCB algorithm is there, because we have to like let go choosing best action, because we need to kind of explore after 10 steps. We need to explore more. Yeah.
So is the spike on the 11th step due to the fact that you in the previous 10 steps you've already explored all the states, so you now know something about which ones give the better rewards, or?
Yeah, you explored, so for the first 10 steps, as we saw here, the weight of this UCB term is overwhelming, and so we are forced to take whatever reward we get, we are forced to take each action at least once. And after that, we have some estimates. And say we have some very high reward for one action, but let me just decrease this. Okay, so and if we hadn't, yeah, that's not really. Yeah, if we hadn't but we don't do any other actions, so the this term of the second term it's accumulates, and we cannot take the best action for long. Many times, because then again this second component will grow, and we should again switch to exploring, and yeah, that happens at 11 steps. Yeah, probably I didn't explain that in haven't got the words to explain it, but hopefully that makes sense. This second component, how it affects the way we explore.
So the log is increasing. The log the log of t divided by NA is increasing until you, I guess, because NA is the number of times you've taken the step.
Yeah. Any action that's not selected increases. So
right, any action that's not selected, yeah.
Yeah, the right-hand term is the uncertainty term. So any action that hasn't been selected, its uncertainty term gradually increases until the sum of it with the Q term becomes the biggest, and then argmax selects it, at which point it'll sample from the distribution and get a better estimate of its true mean. So then if it's a bad action, the Q term will drop down, and because of the fact it's been selected, its uncertainty term drops down as well. And so yeah, that's what you see is any action that hasn't been selected, its uncertainty term steps up until that action gets selected.
Yeah, makes sense. This is great, Arto. Thanks for showing us this, your solution.
Yeah, it's nothing.
Let's see, I guess we should probably stop, because I don't want people to get the idea that they're going to be stuck here for hours and hours and hours. I mean, we have a 2-hour window that we're supposed to meet, so we should probably not go over so much, but it was really interesting. That's why, the discussion that we had after 12 was pretty interesting. So anyway, people who have made slides or whatever, if you would contribute them to the Slack group so that other people can review them, that would be great. And I will post the recording as soon as it becomes available later on today. I'll post it. There's a special slot. Let me just share my screen for a moment. There's a slot in the, sorry, let me get this out of the way. There's a place in the schedule where, oh gosh, sorry, I don't have it right now, but there's a place in our schedule, I've linked to it on the Slack, where there's a column that has the recording. This was something in that I think it was Gautam did in the Python, in the Deep Learning with Python group. He in the schedule, he has a column where he has the recording, a link to the recording, and the password that you need to get it. So I've done that too, and I've put the first link to last week's recording in there already, and later on today, I'll put the link to today's recording in the schedule. The schedule is in our Slack. I put it out in the Slack group, so that's the link to it. Anyway, I hope that was clear. So if no other questions, we can end the meeting, and look forward to meeting again next week. Thanks, everyone.